Hi, my name is Sebastian Robitzsch. I'm with InterDigital Europe, and together with my colleagues from Nextworks, we are presenting a multi-domain monitoring data collection demonstration for the Predict 6G project. The scope and objectives of this demonstration is to showcase how to automate the collection of meaningful data points for deterministic networks in a multi-domain environment. The data points we are focusing on is around the extraction of layer 4 latency data points, as well as sensing related information from a 3GPP domain. The ultimate objective is to feed this sort of information into an AI-driven control plane, and in particular, the data collection management component here, allowing us also to enable the authorization and authentication mechanisms in a multi-domain fashion. We want to ultimately feed the data points that are collected into a digital twin application that is part of the AICP. And this demonstration here aims at the initial integration of the AICP module for authorization and authentication, as well as data collection from a 3GPP technology domain. So the environment that we are playing with here is the 3GPP domain that is illustrated on this slide, where we have a UE, a UPF, as well as a data network. And we have non-3GPP sensors that are hooked up to the UE. We also see the NWDAF that essentially receives various information from the nodes. So we have node information, we have link characteristics, as well as the sensing information from the UEs. We then have an application function that represents the AICP, allowing the extraction of the information from the NWDAF through a nav into the multi-domain control plane that is then utilizing a digital twin to perform its actions. Besides the quite well-known information around nodes, like for example, host name, as well as system information, there's also the sensing data points that are quite unique to this testbed here that are also exchanged through an application function to the AICP. What is illustrated here in this table is the data points that are provided. So we have measurements, of course, around link latency again, and node information. We see at the bottom, for example, CPU, kernel, net, and system telegraph plugins that simply hoover out the information from a Linux node. But we also see in the table on the top that we have radar information, so range as well as point cloud, with data points such as relative power, noise fields, and for the point cloud information, the X, Y, and Z orientation points that are typical for point cloud.
Hi, my name is Matteo Ravalli from Nextworks. So, let's go now with the role of the AI-driven control plane. In this slide, we can see on the right the typical workflow of the service provisioning for an end-to-end deterministic service. When a request is received, per each local management domain in sequence, we allocate the necessary resources, we notify the local AI and DT processes about the service provisioning, and we configure the monitoring. Then we notify back to the end-to-end management domain. On the left, we can see the involved AICP components, focusing on the ones in charge of the monitoring of the data. That is the part of the workflow shown in this demo. In particular, we can see the measurement collection, i.e. the management service of the local management domain that interacts directly with the 3GPP application function discussed previously. Now, let's take a closer look to the AICP data collection module. As we can see in the architecture below, from bottom to up, we have an adaptation layer that normalizes the collected metrics coming from different data sources. Then these data are pushed into a near real-time event streaming bus and into a time series DB for the utilization by the EI and DT processes. We can also manipulate this data to provide aggregated metrics such as mean value and standard deviation. At the top, we have a northbound interface that lets to dynamically create and configure the data sources, the heterogeneous data sources at the bottom, and create and configure per metric permissions of data consumers. So, let's summarize the workflow of this demo. We are going to create a data source that collects the targeted metrics of a FreeGPP technology domain. Then we create a couple of data consumers with different permissions to show the per metric authorization and authentication mechanisms. Finally, we visualize the retrieved latency and sensing data.
On this integrated demonstration, we have here again the topology from the 3GPP domain. We have the UE, UPF, and data network, and data from all three nodes are pushed into NW-DAF. Moving on now to the actual demonstration. So we have again the 3GPP domain with the UE, UPF, and data network. They share the node information to the NW-DAF, and we have the sensory information coming from the UE that is also shared with the NW-DAF. On top, there's a dedicated application layer probing framework composed of a client and a server, allowing us essentially to measure round-trip time and link latencies. How this client works, or this framework, there's a probe sent from the client towards the server, including its host names and the time. The probe is received, a PONG is being sent back, again with the host name then of the one that sends it back, and we can immediately calculate the elapsed time for the link latency, and based on the PONG, we can calculate the time for the round-trip time between two nodes, which is then shared to the NW-DAF, of course. What we have here is an interface into the NW-DAF, a web-based interface, where we have all three nodes again. We see UE, we see the UPF, as well as the data network. So we have link latency as well as round-trip times. We have CPU utilization, and we have the sensory data on the bottom left graph. On the right, we see that the UE has the ARIA client as a service installed, as well as the measurement service, the sensing data collection aggregation function, and the UPF has both ARIA client, ARIA server, and the server itself. So first, the SDCAF sends or collects the radar information and sends it to the NW-DAF, and we have here the range profile and the radar range, which we on the bottom left, that is collected from the directly from the UE. For the ARIA client, we can see that the PONGs are being sent to an address, which is in this case the UPF, and this this ping, so this probing ping includes the host name of the UE. Once this message is received, we can calculate the link latency immediately. Of course, all nodes are time synchronized. And once the response is being sent back, the PONG is received, and we can measure the round trip time a particular packet or a particular link has for a UE.
In Influx, we can see all the metrics of the sensing-enabled FreeGPP technology domain. There are node information, link characteristics, and sense information. We show the latency graph as an example. Now let's jump to the AICP data collection API and its Docker services. At the beginning, all the telegraphs are done. At this point, we send a POST request to create a data source for this technology domain. We specify the metrics of interest in the request body. The response contains the ID of this data source, and the corresponding telegraph is instantiated. So, among all the metrics provided by the FreeGPP technology domain, in Kafka we can see the only ones collected by the monitoring platform, i.e. the sensing information and the latency. We show a latency message as an example. Now we create the first data consumer by sending a POST request with the consumer info in the body. The response contains the ID of such data consumer that we're going to use for the next POST request to enable read permission on all the metrics collected by the monitoring platform. To automate the verification of the differentiated access to the data, we instantiate a proper and distinct telegraph which fetches the right data from Kafka and prints them out in a log file associated to the data consumer through its ID. And we can see in real time that the log file is filled up with all the metrics for this data consumer. Finally, we create the second data consumer and enable the read permission for only the link measure. And as we can see, its corresponding log file is filled up with only the link matrix.